Welcome back to Module 3. We are continuing the discussion on how to represent a particle in quantum mechanics, and we are trying to find out the analytical solution to the wave packet dynamics, and we have so far seen if I have a stationary wave packet, Gaussian wave packet, how it should behave as a function of time. As the time progresses, the shape of the Gaussian, how it's changing. We have seen that it's broadening and the amplitude also decreasing. So next we'll move to traveling Gaussian. The Gaussian which will travel as a function of time. Now, as I mentioned before, a traveling Gaussian, in this analytical approach, I just remind that in this analytical approach, I need the initial wave function, initial Gaussian wave function at t equals 0, because from that I can find out ak, and then I can insert that function, ak function, and I can get the wave function, which the wave packet, which will how does it look like at a different time. This time dependent wave packet I can find out. Now it is just one example with the Gaussian function. If we start with Gaussian function, we can get this analytical solution, but this doesn't mean that for every situation I'll be able to get an analytical solution, and these are the things which we'll learn very soon. But so far we are talking about free particle. Free particle, which means that the particle is not experiencing any potential. So previously I told already, this is the normalized traveling Gaussian. This part is the Gaussian function and it is traveling. This part is contributing to this movement, and we have seen that this is the envelope function and this is the carrier wave of the wave packet. So this is called carrier wave of the wave packet, and this is the envelope function. So what we did before, we will first find out ak, because that's the way we are going to work on. We need this ak, and with the help of Dirac delta function, we have seen that ak can be represented as 1 by 2 pi minus infinity to plus infinity psi x0 e to the power minus I kx dx. This is going to give me ak. So let's plug that in. This initial Gaussian wave packet, I can plug that in and I can get this 1 by 2 pi 2a by pi to the power 1 by 4 integration limit minus infinity to plus infinity e to the power minus a x square e to the power I k naught x. You can remember that k naught was the average of all k. So in order to get this initial wave packet, how does this wave packet look like? I have an envelope function and then carrier wave. So this is what initial wave packet is, which is nothing but the particle in quantum mechanics. A particle in quantum mechanics is the localized matter wave, and this is localized in space, localized matter wave. So we should view particle as this. This is just an example. It can be Gaussian It can be some other shape. Shape can change, but it should look like this. And K naught was kind of an average of all Ks. So K1 plus K2 plus K3 like this, all components. And here, because it is minus infinity to plus infinity, we have to add them and then add the total number. So that was the K, the meaning of K naught. It was the average of all this. That's the, and that is the K represented by the carrier wave. So this K naught and then e to the power minus I kx dx. We will follow the standard Gaussian integral. The reason why we take the Gaussian shape is because the integration would be much simpler to deal with. Otherwise, integration is, we need to use numerical method to integrate it. So I have K plus K naught x dx. So standard Gaussian integral will give me pi by a e to the power minus k minus k naught whole square by 4a. And if this is k ak, then I'll be able to plug this in here and I can get the wave function. Ak is, I'll write down the constants first. So all these constants are going to be 1 by 2 pi, then 2a by pi, then square root of pi by a, and then I have this integrand e to the power minus k naught square divided by 4a multiplied by e to the power. So we'll place them, and we remember ek, we had a value ek, and ek was used to be, this is the kinetic energy of the particle, and the kinetic energy of the particle was given previously. So we can use that ek value, and we can reduce this equation to following. I do not need to use the same, so I can reduce it to plus I k x minus I h cut k square t by 2m dk. So this is the integration we have to perform analytically to get the final wave packet. Now if we look at this expression, the exponentiation, this can be reduced very easily. We can reduce it in the following way. I have minus k naught whole square divided by 4a plus I kx minus I h cut k square t divided by 2m. That's the exponentiation I have. What I'll do, I will just rearrange this one a bit. K square minus 2 k naught plus k naught square divided by 4a. I have negative sign here. Then I have plus I kx, and then I have minus I h cut k square t divided by 2m. So this can be written as minus k square within bracket 1 by 4a plus I h cut t by 2m. This is just tedious mathematical derivation, that's all. There is nothing very complicated here. K naught by 2m minus k naught square by 4a. So this can be used in this exponentiation, and if we do that, then I have all these constant parts, and then I'm not writing it, minus infinity to plus infinity, and then I have e to the power minus k square 1 by 4a plus I h cut t by 2m plus k I x plus k naught by 2a minus k naught square by 4a. Then I have dk, integration over dk. So if I do this integration, what I get, I can simplify these constants, and finally I get 2a by pi to the power 1 by 4 e to the power minus k naught square by 4a, and within square root I have 1 plus 2I h cut t a by m, and then e to the power minus a x square plus I x k naught plus k naught square divided by 4a. So I have this one divided by this 1 plus 2I h cut t a by m. This is the exponential function we have. And if we have this exponential function, then this part, this minus this part minus a x square plus I x k naught plus k naught square divided by 4a, this part can be written as a multiplied by I x plus k naught by 2a whole square. So if we do that, then I'll be able to get the final expression for the Wavepacket as 2a by pi 1 by 4 e to the power minus k naught square by 4a, then square root of 1 by 1 plus 2I h cut t a divided by m, and then exponential part I can write down like this way. It is e to the power a multiplied by ix plus k naught by 2a whole square divided by this term 1 plus 2I h cut t a by m. So this is the final expression we get for the wave function. With this final expression, once we get the final expression, we know we are interested in the density, because the wave function is not going to give any meaning until I convert it to the density and then look at the density, how the density is changing. So we have got the final expression for the wave function, and we are going to check the density, how the density is changing, because density is something which can be connected to the experimental observable. And when you look at the density, so in order to find out the density, what we'll do, we will assume that, again as we did before, 2 h cut Ta by m equals b. We will assume that, and if we assume that, then I'll be able to write down the density in this following form. And the reason why I can write down the density in following form, because I get this wave function, this Wavepacket xt Wavepacket, as follows. It is going to be 2a by pi to the power 1 by 4 e to the power minus k naught square divided by 4a, then square root of 1 by 1 plus ib, and then e to the power a ix plus k naught by 2a whole square divided by 1 plus ib. So this is the wave function we get, and from that wave function I can find out the density. And once we get this density, we can rewrite this expression for the density as follows. We will rewrite this part. This part we have to simplify here, and we will follow this simplification. This a ix plus k naught by 2a whole square by 1 plus ib plus a minus ix plus k naught by 2a whole square by 1 minus ib. This will be simplified as follows. This is going to be nothing but a by 1 plus b square 1 minus ib multiplied by ix plus k naught by 2a whole square plus 1 plus ib into minus ix plus k naught by 2a whole square. So this can be simplified further. 1 plus b square minus 2x square plus 2bx k naught divided by a plus 2 k naught square divided by 4a square, which is nothing but minus 2a by 1 plus b square into x square minus bx k naught divided by A minus K naught square divided by 4A square. This can be written as minus 2A by 1 plus B square x square minus 2x K naught B by 2A plus K naught B by 2A whole square minus K naught B by 2A whole square minus K naught square divided by 4A square. So finally, if I reduce it further, I get 2A by 1 plus B square x minus K naught B by 2A whole square minus K naught square by 4A square multiplied 1 plus B square. So this is nothing but 2A by 1 plus B square minus 2A by 1 plus B square multiplied by x minus K naught B by 2A whole square plus K naught square divided by 2A. So we get this simplification, and we can plug this in here, and we will get we will finally get this form, this Wavepacket form. We have simplified this part, and will get this psi Wavepacket xt equals 2A by pi to the power half, then e to the power minus K naught square by 2A, then square root of 1 by 1 plus B square. Then I have this, we have reduced it already, e to the power minus 2A x minus K naught B by 2A divided by 1 plus B square, then multiplied by e to the power K naught square by 2A. So this part will cancel out each other, and finally I get a simplified form of this big expression as 2A by half 1 by 1 plus B square, then e to the power minus 2A by 1 plus B square x minus K naught B by 2A whole square. So I get this final expression for rho xt, this Wavepacket rho xt. And one thing I would like to now so this expression, this is constant, this part, the initial part is constant, and then you have x squared. So basically what I have right now is the Wavepacket which is having a Gaussian shape again, but there is a difference, and the difference is if I had e to the power minus, let's say, some constant a x square, this is a Gaussian function which is centered at x equals 0. But if I have e to the power minus a x minus b whole square, then this Gaussian function will be centered at x equals b. It's just shifted from the center position x equals 0 to x equals b, and that's the meaning of this function, this Gaussian function. And similar Gaussian function we have here. So what we see here is that the center of the Gaussian is changing in this case, and the center of the Gaussian will be represented by xt, because it is t dependent center. Xt is nothing but k naught b by 2a. That's where the Gaussian center would be, and we can see that it is, if I use the b value, previously we have used the b value and a value, we know that a value, both are known. So b value was, we assume that b was, so this is going to be k naught, and b was 2 h cut t a by m 2m. So in the end what I get, the center of the Gaussian is t dependent, and I get k naught h cut t divided by m. What we observe here, this xt is the center of the Gaussian. The Gaussian is now is shifting. So at t equals 0, I started with a Gaussian which was centered at x equals 0. Now at different time, let's say at t time, the Gaussian is not centered at x equals 0 anymore. It is centered at this point, which is xt point. So it shows that the Gaussian is traveling over time on the x axis. On the x axis is slowly traveling, and center of the Gaussian is traveling. And if xt, the center of the Gaussian, is traveling like this way, then I can find out dxt dt, center of the Gaussian, center of the envelope is changing, envelope function is propagating. Now because dxt dt is finding out the velocity of the envelope, velocity of the envelope is given by the group velocity. That's the definition we have given. Velocity of the envelope in a Wavepacket is given by group velocity, which is now nothing but k naught h cut by m. What we observe here is that Wavepacket, that particle which is represented by the Wavepacket, is now traveling with this k naught h cut by m velocity, the group velocity. I have observed that the particle which started with a position at x equals 0, the center of the Gaussian started with x equals 0, it is now propagating along x axis as a function of time, and we have found that the group velocity is represented by the velocity of the center of the envelope, and which is nothing but k naught h cut by m. So we will stop here, and we will meet again in this module. We will continue this module in the next session.